Today we have a great speaker, which is Ory Band from Kin. Ory is a blockchain engineer. At the past year, he worked on top of Stellar, and in the past few months, he's working on a fork version of Stellar as part of the Kin blockchain project. He's the best person to speak about Stellar, and today he's going to give us an overview of its history, architecture, and talks about its decentralized consensus model. So, Ory, come, the stage is yours.
Hi, everybody. Thank you for joining us this evening. So I'm Ory, and let's start. Okay, so the Stellar blockchain and the story of decentralized consensus and federated consensus. The topics that we will talk about today, first of all, I will introduce a few terms just to make sure that we are all aligned on the same subject, and tell you a story about decentralized consensus. Then we will talk about the product and business requirements of companies that can benefit from decentralized consensus systems. I will introduce what a permission blockchain is, and we will also compare it to the popular permissionless blockchain today. And then the primary part of the presentation will be to do a deep dive into Federated Byzantine agreement and its first implementation, which is the Stellar consensus protocol. And to wrap up, we will also introduce Stellar's ecosystem because it has some interesting points to look at. So let's start. A little bit about me. As Nathaniel said, I'm a backend engineer at the blockchain team at Kin. I've been working on Stellar technology since the end of 2017. I have also worked on the Kin token sale that we've had. I've written multiple smart contracts, the sale contract itself, vesting contract, and also multi-sig contract. And lately, I've also done a deep dive into migrating our blockchain from being an ERC20 token over Ethereum into our own blockchain. The specific topics I'm working on are spam mitigation, scaling, and swaps for migration. So let's start with an introduction. So I'll start with a few terms just to make sure that we are all aligned. The first term I want to introduce is consensus and what it means specifically in the crypto industry. So consensus means, in our point of view, to reach an agreement between multiple components in a system. Specifically in the blockchain industry, the thing that you want to agree upon is pretty much having nodes in the system to agree on a single on the same contents and updates of a ledger of blocks. For example, let's take a simple case where we have a distributed system. Where we want to reach a case where if some node has received an input, let's say the input value is X, and he wants to share this value across the rest of the nodes in the system. So to achieving consensus means that eventually after a specific process, the entire system agree on the same value X that is the result of an input of one of its nodes. So if a client, for example, polls the system, no matter where, from which node, the system will reply the same value, in this case, X. Now for another term, which is important to be familiar with before we continue, and it is fault tolerance. So fault tolerance is a property that enables a system to continue operating properly in the event of a failure in some of its components. For example, let's say that one of the nodes in the system crashed. Its application suffered a bug and it is no longer responding. So a fault-tolerant system will still be able to achieve consensus despite such failures. To reach from a state where one node has received an input to a state where other well-behaving nodes which haven't received the fault to agree on the same value. Specifically, in decentralized distributed system, we mostly care about a hardening of the fault tolerance term, which is called Byzantine fault tolerance, also BFT. The reason it's called Byzantine is because the problem it talks about and solves is being told as a story about Byzantine generals that need to agree upon a certain attack plan in order to conquer a city, and they have to coordinate and agree on the same attack plan. Where there might be cases where some of the generals are traitors. So the definition for Byzantine fault tolerance is that it is already a fault tolerant system, but in addition, there is imperfect information whether a component has failed. Specifically, components can be entirely unpredictable. They can either suffer a bug or crash, just like in the previous example. They can be malicious and provide inconsistent replies to multiple parts of the network. They can say to one part the value X and to the other part the value Y, and it doesn't really matter if the reason is malicious or it's by mistake. So a Byzantine fault tolerant system is a system that can still cope with failures in it, even without knowing which node has failed or not. This is an example taken from an academic paper that introduced the first solution for the Byzantine fault tolerant problem. The solution's name is Practical Byzantine Fault Tolerance, or BFT in short. It shows the distributed system here includes a commander and 3 lieutenants, where 2 lieutenants and the commander are honest and haven't suffered any faults. But the 3rd lieutenant did, and he's lying or providing false or just wrong information to other nodes in the system. So the commander, for example, is trying to share and agree upon a certain value V, and the 2 honest nodes over there are indeed sharing the same value as well. But the faulty node, the faulty lieutenant, which is a traitor, is sharing the wrong information X. So a Byzantine fault-tolerant system is one that can still have a rich consensus among its well-behaving nodes, its honest nodes, even though there are bad actors in it. This is the most difficult fault tolerance version to solve. There are multiple solutions for this today. PBFT is the first one. So these are the terms that I wanted to be aligned on. Now we can continue with the story and actually start the presentation itself. So I want to tell you a story about decentralized consensus. So it starts like this. In the beginning, the world is centralized. It's not actually in the beginning, it's also today. Today we live in a centralized world where multiple parties that might want to collaborate but it is still possible that they have conflicting interests, cannot do it without using some sort of middleman. For example, if there's some business who wants to exchange multiple payments between it and other businesses, it cannot do it without an intermediary, a bank or a chain of banks that will approve the payments. Governments have control of currencies, so exchanging payments needs to be under the laws that the government, the centralized authority, approves. And it also dictates other laws. It also controls the monetary policy and so on. If you want to execute a certain contract between you and multiple other parties, you will probably need a lawyer or an escrow. This results in a chain of middlemen and a chain of fees that it would have been very, very nice if we could have go around this problem. Specifically regarding infrastructure, today most Byzantine fault-tolerant systems are centralized in the fact that, by example, that in order for them to actually be Byzantine fault-tolerant, there needs to be a central authority which dictates the players that take part in consensus. PBFT, which I've introduced before, is a solution. There are additional ones that have been introduced in the past decades. Paxos Ruffed. If anybody here is familiar with Consul, the configuration system, it uses Ruffed to achieve consensus. In centralized the Byzantine fault-tolerant system today, so like as I said, owners are predefined. And it's usually belong to the same entity or a very small groups of entities that have some sort of agreement beforehand. That's pretty much it. But then in 2008, 2009, Bitcoin arrived to the world. And Bitcoin, and specifically the way that it achieves consensus, which is called Nakamoto consensus, the whole proof of work thing, he showed the world, Bitcoin showed the world that for the first time, we can have a distributed system that is still Byzantine fault tolerant, but instead of having it being controlled by a single entity, in most cases, it actually is operated by multiple entities, which have possible conflicting interests. The properties of such a system is that for the first time you could enforce a set of rules, for example, a payment network such as Bitcoin, and it was still distributed, Byzantine fault tolerant, and the important part is that it was decentralized. That is, there are multiple parties that take part in the network, and that middleman that I've told you about before, well, you might no longer necessarily actually need to use it. And you could avoid those fees and other problems. Let's talk about other features that were introduced with proof of work and Nakamoto consensus. Can anybody here answer the question? There are multiple answers to this. What other features? Okay, I will translate what you said. Not just a currency, you could enforce a set of rules. It's pretty much what I said earlier. Currency is some sort of a rule system. What else? For example, it's another set of rules. Okay. What? Yes, great question. It's actually one of the bullet points here. So these are additional features. This is not the entire list. There are other properties. These are just the one that I thought were important for this presentation. There's no double spending. Information is replicated because, well, distributed systems, specifically Bitcoin, is a replicated state machine. Once the information is recorded, it's being replicated into multiple places, so there's no single point of failure. The information is immutable once blocks achieve a certain amount of confirmation. Information is transparent, it is anonymous, and it's quite easy to audit it. In addition, there's a layer of authorization achieved by cryptography, the whole private-public key thing. And there's also another feature, which is called permissionless. And on this property, I want to deep dive today. So what does permissionless actually mean? So the definition goes like this. In a permissionless blockchain, anyone can join the network and participate in consensus without censorship. Censorship meaning to having some authority that can block you or delay your participation in the network, specifically to achieve consensus. So the question I want to ask is, why? Why is Bitcoin and other proof of work system have this permissionless property? Why is it there? Can you think of an answer? Yes.
Because otherwise there would be a centralized party giving permissions. Because you don't have a centralized party giving permissions, it's a permissionless.
I think it's the other way around. I think everything you described is in order to be permissionless.
No, this is not the answer. This is not the reason. There is a reason. And so, yes.
Why is the name permissionless?
Yes, why is Bitcoin open for everybody?
Well, the idea is, especially since when Bitcoin specifically with after the financial crisis and the banks and the story with the banking cartel and so on, and so then you have access to a money system that doesn't need a central player to determine who has and who doesn't and can inflate money at will through fiat and all that.
Yeah. Yes. One of the answers is that it might be a bit inflammatory to say it's anarchistic. This is one of the reasons, but there's a technical reason. Sorry? Okay. If you think...
We need to decide what permissions to create. Everybody has to agree on the permissions.
This is not exactly what I was directing at. What I was directing at. There's a very important technical reason that Bitcoin and other proof of work systems are permissionless, and the technical reason, not the political reason.
No, I was going to say with the Merkle, you test the results of the cryptographic puzzles, right? So maybe
I think you're going in the direction, yes, for the technical reason, not the political reason. So permissionless is not actually a feature. It's a requirement. And it's a requirement for proof of work to actually work well and be secure. And proof of work exists because this is the proven way that the most popular proven way that we have today for achieving decentralized consensus. Because in proof of work, the larger the network, the more secure it becomes. This is the technical reason. Everybody here, is anybody here not familiar with the majority attack, with the 51% attack? In a very short way, the attack means that if an attacker gains majority over the nodes that participate in consensus over the network, he can pretty much do what he wants. He can delay transaction, block them completely. So he can do denial of service. He can change the history and practically then do double spend. So in proof of work networks, a smaller network doesn't have the property where it is very costly for an attacker to act. In Bitcoin today, it is secure because the hash power of miners is so large that it is very, very costly to attack the network. But in the early days, in the beginning, or for a very young other proof of network system, it doesn't require, the size of 5 nodes or so. It doesn't require plenty of resources. Yes? Just a second. Yes.
Wouldn't it cost just, I saw something like $50,000 an hour or something like that to have temporary CPU power for 51% attack, and all of the processors together cost like just, I don't know, $4 billion. That's a lot of money, but not a lot of money for a government or a big institution.
In Bitcoin?
Yeah.
I'm not very familiar with the pricing and numbers, but I'm not entirely sure. It is today. For example, for a block that is quite old, let's say a few days or so, it takes plenty of time to. It's practically impossible. I don't want to go into the argument of how much and if it's possible because it's not the point, but. The point is that if the network grows big enough, it's okay. But if it's not big enough, it's proof of work networks are susceptible to the majority attack. So the point is that a permissionless system, it's not just a feature, it's a requirement for a proof of work system to work, to actually be secure enough to achieve a decentralized consensus. In addition, it's not just a requirement, but it is also a compromise for proof of work because proof of work with using the permissionless property, a proof of work system achieves security while it's sacrificing other things to have this security. So my question is, what things does permissionless and proof of work compromise on to have this security? Wasteful in what way?
Energy-wise.
Good answer. That's one of the answers. What else? Let's include this under energy, but like scale. Fine. Yeah. What do you mean by difficulty to enter?
At the moment, it's really difficult to get into mining Bitcoin specifically.
Okay, so there's the whole mining thing, mining entry price or something. What are the compromises? The question was, what are the compromises for proof of work and specifically the permissionless part? What did proof of work compromise on in order to be secure using permissionless? Yeah.
First of all, it's probabilistic. It's not actually solved the consensus. The commodity consensus is not a solution for consensus in the computer science sense, because you still need to agree on the fork, on the right fork. And the other, because you have blocks, and so you have delay.
Delay? What do you mean by delay?
It's not real time, it's not real interactive, because you have some delays between blocks.
Okay, so I think what you're trying to say is that the clearing time for transaction is not as fast as it could have been if there wasn't mining, for example. Yeah, okay. So all the answers here were correct. There are probably others. So you've said scalability. There's a limit on the block size and also on the rate limit of adding blocks. There's wasteful energy consumption, be it electricity, time, other sorts that can translate to money. Also, there's a trend currently, a thing that is called the trend towards centralization, where miners join into groups and pools and cartels, which has its own impact of politics on the network. Like there's this tribunal of the developers, the users, and the miners, and it became quite difficult to introduce new development changes and updates to the network without the agreement of miners. So they've turned into this whole political group that can affect the network. It might be, but you cannot deny that you're correct, but you cannot deny that it creates some encumbrance on the system on other aspects.
As soon as the security is becoming more secure, also all these issues are becoming.
It depends. The question was: are the issues introduced here becoming more severe as the network goes larger? And the answer is: it depends on how Bitcoin will move on from here on. There might be changes that will be introduced in the future, but currently. These are the problems. These are some of the problems that Bitcoin deals with. Also, another thing that I've skipped is that because you need to incentivize miners to secure the network, it pretty much narrows down the way that the multiple ways that you can provide incentives in the network. You have to assign a stash of resources, of tokens in the network that needs to be assigned to miners. If, for example, we could have skipped the entire mining thing, we could have made much more flexible choices in how to distribute tokens and cash in the network. For example, we could have used inflation. We could have redistributed the fees after a certain time back to all the users. The whole mining thing provides a bit of extra inflexibility to the network. But it still works. Yes. Sorry? I'm sorry, are you answering which question? There are other shortcomings. You're correct, but let's move on. Proof of work works, and it's currently a very popular solution. And it is okay for proof of work to have this compromise. So I want to introduce another question. Why is it okay for proof of work to introduce this, to have this compromise? And what I want to get at is that in order to understand why it's okay to proof of work to have a permissionless system and to compromise on permissionless, is to take a look at what, what exactly is the product of proof of work systems, of Bitcoin, of Ethereum. So for Bitcoin, the product of Bitcoin is that Bitcoin wants to be a medium of exchange, digital cash, and/or a store of value. For Ethereum wants to be some sort of world computer and a decentralized app and contract platform. So these requirements eventually lead to this property being part of the system, to be an inherent part of the system. However, not all products, there are other products that can benefit from decentralized consensus as a subject without having to make this compromise. Specifically, to compromise on the permissionless part. They can make other compromises, but still benefit from the decentralized consensus. So now that I've given you a short story about decentralized consensus and where we are today, I want to introduce Stellar, the company, and talk a bit about it and dive a bit deeper into its business and product and understand why they are going, why they are diverging from the way that other decentralized consensus systems such as proof of work have gone. So a bit about their history. Stellar was founded by a guy named Jed McCaleb. He's the guy that created the eDonkey network. If anybody here used the email client, the client is using the network that he created. He also founded Mt. Gox. By the way, does anybody know what the acronym for Mt. Gox means? Yeah. He said Magic the Gathering online. Originally, before 2010, Mt. Gox was a trading card website for the trading card game, which is called Magic the Gathering Online. And it was an exchange, so we added the X. And then in 2010, he changed it into a Bitcoin exchange and eventually sold it a bit before the crisis happened. I think in 2011, 2012, the crisis actually happened, so he's the one who originally created it. He co-founded Ripple, the crypto company that is attempting to, whose one of its goals is to replace SWIFT, the credit card clearing company system. It was in 2010. So a bit about the timeline of Stellar. So Stellar was launched in 2014. It was originally a fork of Ripple. Jed left Ripple and founded Stellar. It introduced a new consensus algorithm in 2015, which is the one that we will deep dive into later in this presentation. And from 2016 until today, they've announced multiple partnerships, specifically with IBM for cross-border payments in the South Pacific, and also another partnership with Keybase, which is a company that's trying to abstract the whole cryptography complex part from humans and use real-world IDs, such as emails. So they'll announce a partnership with them as well. Exactly this. They're trying to make it simpler to use crypto without thinking about keys. That's pretty much. The guy who wrote the Stellar Consensus Protocol white paper is also a member of Keybase. They have some good relationships there. Okay, so a little bit about their business model. So Stellar are trying to be a payment platform, but they are specifically targeting financial institutions and specifically in developing countries. The story goes like this. Today, about 2.5 billion people do not have access to banks, specifically in developing countries, and it's become quite expensive to transfer money also inside, but in and out of these countries. It's pretty much expensive to be poor. For example, transferring a certain amount of funds incurs about 20% fee in certain places. So they are trying to solve this problem using cryptocurrency. They are targeting banks, nonprofits, and microfinance in developing countries. They also have an integrated distributed money exchange inside their protocol. So you can create assets and trade them with other assets over the network without having to rely on a centralized entity, like an exchange on the network. And lately, they've also started to become an ICO platform. I think last year there was an ICO for a company called Mobius over Stellar. So these are pretty much the things that Stellar acts on today. Yeah. So after going over the business model of Stellar, if we think about it, we can see that Stellar can, of course, benefit from decentralization and centralized consensus to go around all the fee problem. But if you think about it, Stellar mostly require institutions to join the network. Not everybody. They mostly care about banks, about microfinance, and so on. So here is where the permissioned decentralized consensus term goes into play. And I would like to define it, and then we'll compare it to permissionless blockchains. Are there any questions before I continue? Okay. So what is a permissioned blockchain? So in a permissioned blockchain, entities require privilege in order to join the network and participate in consensus. This is different from before, in that before you didn't need any sort of privilege. So this privilege can be total in the network or flexible. It depends on the flavor of the blockchain and technology that we're talking about. But in general, it means that if we have a decentralized network where multiple entities would like to collaborate, so you need to have a predefined list of known nodes. The nodes need to be verified and registered beforehand. For example, in this case, let's say A would need to trust B, C, and the B, C, and D businesses, other businesses. And B, for example, need to trust A, C, and D. As I said, the amount of predefined trust that you need to have is not, it doesn't have to be total, it can be flexible. So for example, B doesn't have to trust everybody, it can only trust a subset like C and D, and not even be aware of A in the network. It depends on what technology we're talking about. It pretty much depends on the platform. Today, there are multiple solutions. There are other, in addition to what I'm showing here, that are using flavors of permissioned blockchain. The logo on the left there is Hyperledger by IBM, which uses PBFT, practical Byzantine fault tolerance. Over there, you need complete permission for nodes to join the network. The one in the middle is Ripple, and this one is Stellar. So let's compare the properties of a permission blockchain to a permissionless one. Does anybody here have any idea what properties might be different? Scale? Consensus, of course, consensus is different. Sorry?
Also, between the permission system, how you can change who has permission. So the system that you use for that.
So you said that the way that how you change trust?
Yeah, I mean, for example, you didn't have it up there, but maybe EOS would be something like that too, in the sense where you're voting in the permission person.
No, what I was asking is in what ways permissions are different from permissionless, not between multiple permission. Yeah.
In permissionless system, everybody is equal except the minus maybe. But in permissionless, in permission, we have first-class citizens and second-class citizens.
Okay. What other answers? Yeah.
Latency is much lower.
Oh, yes, yes. Because there's inherent trust, unlike in permissionless, where there is zero trust, and you need to prove your honesty by solving a riddle, for example.
This is skip mine.
Sorry?
Skip mine. Don't need mine.
Yeah. Yeah, you do not need to secure the network the way proof of work does, because there is inherent trust between at least some of the nodes in the network. Yeah, yeah. So, yeah, so pretty much summarizing the answers here. In order to secure the network, there is a very low participation cost. There's no mining. Also, by the way, if we're talking about proof of stake, there's nothing to stake, because you don't need to prove your honesty by staking something. The network, also another property, is that the network doesn't actually have to be large in order to be secure. There's no, the majority attack thing is irrelevant in this case. No matter if the network size is the size of 5 nodes or it is the size of 5,000 nodes, since there is inherent trust between nodes in the system, it doesn't really matter how big it is. So, sorry? The what? yes, this is correct. And of course, you need to make sure that you're trusting reputable and proper entities. There's also, compared to permissionless, it can achieve higher scale much easily, specifically have very low block time, ledger update time, and have higher throughput, increasing or decreasing the block size. Doesn't incur the same political questions that might be in Bitcoin, for example. Also, if you think about it, you don't necessarily need a token. I mean, if you're talking about cryptocurrencies, there's another question. But if you want to achieve consensus or something, think about like a database. You don't really need to exchange something that has a value in order to agree on something. In proof of work, you do. You have to, because this is the way that you incentivize securing the network. But if there's inherent trust, there's nothing really to exchange that. It is not necessary to exchange a token of value. It is not a requirement.
They need some sort of incentive.
If we are talking about a cryptocurrency, then yes. But if you just want to achieve consensus over something, if you have inherent trust,
Anyone who's going to run any node, even if it's permissionless, has some sort of incentive to run that node.
this incentive does not necessarily have to rely on tokens. It can be on something else. Let's say it can rely on other business initiatives. Also, and because there is no mining, it gives you many more options to create an incentive model if you wish to. For example, you can use Stellar uses inflation, and it uses it to also to redistribute fees back to the users. So this is pretty much the entire introduction where I've introduced decentralized consensus, talked about the product requirements for decentralized consensus systems, specifically focusing on Stellar and introducing permissioned. So now I think we are ready to deep dive into the implementation of one of these permissioned technologies. So I'll begin with a bit of a background story about Stellar and why they have chosen this path. So remember that Stellar forked from Ripple. So back in December 2014, they had a pretty severe hard fork incident where they had about an 11-hour long hard fork, where at the end about all the transactions during this time could be double spent or could be entirely lost. There was one exchange that supported Stellar at the time that pretty much said that it is not liable to anything that resulted from this hard fork because it pretty much didn't have anything to do in order to solve this. It was a pretty severe issue. As a result, Stellar were forced to run in a centralized way using a single node until they provided a fix, which is the new consensus model that they have, but this was only about half a year afterwards. To understand why this happened, I would like to explain a term called the FLP impossibility. FLP doesn't really stand for anything important there. It is just the name of the researchers that proved the theorem. It pretty much goes like this. In asynchronous distributed systems, it talks about three properties: fault tolerance, liveness, and safety. It goes like this. So there's the property of fault tolerance. There's a property of agreement, also called safety, which means that at any given point in time, the system agrees on a single value, achieves consensus or agreement over something. And there's also a third property, which is called termination or liveness, which means that the agreement process is finite and is time-bounded to end. So the theorem talks about these three properties: fault tolerance, which we are already familiar with; agreement, which is that the system agrees on consensus at any given point in time, agrees on a value, single value, sorry, and that the process actually terminates. And there is no state where you ask the system what is a value, and they say, I don't know yet because we haven't achieved the agreement. So the theorem, the FLP impossibility, says that you can only pick two out of these three properties, not all. This is pretty much also resembles the CAP theorem, which talks about asynchronous storage systems. It resembles it in some way. So pretty much, if you have this triangle, you can only pick one of the edges, not the entire triangle. So Ripple and Stellar, before they introduced their new consensus model, looked like this. They favored, their consensus model favored fault tolerance and termination over agreement. The reason the hard fork happened was because Stellar's developers tweaked a parameter which made nodes terminate their consensus when there was only 80% agreement in the network, so, and then move on to the next stage. This was the reason that it happened. Can you think of a reason why it happened? I mean, why did the system even allow for this to happen? Sorry?
They wanted to satisfy the third termination.
Yes, because it had to end in some way, and it couldn't wait until infinity to achieve agreement for the entire system. So the way that they achieved consensus back then was that they favored fault tolerance and termination, which practically means that you have to, the way Ripple implement this is that if you don't achieve agreement by the end of the agreement process, which has to end because it favors termination, you just repeat the process multiple times with exponential probability, reaching 1, almost 1, over multiple retries. So if you didn't succeed over the first attempt, just try another one, and there's very high probability that in the second or third you will achieve agreement. But apparently, after Stellar tweaked some parameters, it wasn't so. The new consensus model today pretty much reverted the edges, and now it favors agreement over termination. The result of this is that consensus isn't guaranteed to terminate, but at any given point in time, there's agreement in the system. There's no chance that there will be safety issues, will there be some sort of partition where one part of the system says 1 and the other part of the system says 2. By the way, do you know what properties Bitcoin favors? Agreement? Okay. Does anybody here think otherwise? Bitcoin actually does favors termination, and it is evident is because there are hard forks in the system. There are cases where you have forks where one part of the system still haven't converged on the longest chain, for example. I would like to introduce Federated Byzantine agreement, which is the theoretical Byzantine fault tolerant solution for Stellar, and the Stellar consensus protocol is actually implementing this agreement and consensus model. So the properties. The properties for Byzantine, for Federated Byzantine agreement is that, first of all, it's Byzantine fault tolerant, it is decentralized, it has lower latency as a side effect of being a permissioned network. It has flexible trust, which I will focus on in the forthcoming slides and elaborate on it. It pretty much means that nodes don't really require total familiarity with all nodes in the network, only part of them. And they don't need to trust everybody, only part of the network. Also, this scary buzzword, which is called asymptotic security, is just another way of saying that the network is not susceptible to majority attacks. It doesn't really matter, it doesn't really impact the security if the network is small or big, which is a result of having the network having inherent trust. the white paper have this nice comparison table where it is compared to proof of work and proof of stake and the classical Byzantine agreement solution. Well, so proof of work, of course, is decentralized, but it doesn't enjoy the property of having low latency and having flexible trust in the network. You always have to trust the miner that solved the cryptographic puzzle. You cannot decide not to choose it. The protocol decides this for you. And it's also not asymptotically secure in a way that young and small networks are not susceptible to majority attack. For proof of stake, there's also no flexible trust because you always have to trust the people, the entities that have the most stake.
You mean the opposite? It's trust. You have to be trustless.
No, my point is that you don't get to decide who to trust. The protocol decides. And in proof of work and proof of stake, you decide either the one who have actually proven his work or the one who actually proved that he put some stake. You cannot decide whether to trust them or not. In permission, you do. The classical Byzantine agreement solutions, PBFT, has all these three options, but it is, of course, centralized. Tendermint is another solution. We will not focus on it today. And SCP, which is the reference implementation for Federated Byzantine agreement, claims to have all four of these. This is I understand what you're saying. This is correct, but it's more of a political statement. If you consider only the technical requirements, so it's not really. There's nothing to argue about. It's an interesting point. You're welcome to come and discuss with me about it once we're done. It's just a screenshot from the white paper. It's something to think about. I want to give a top-level definition that roughly explains how the consensus actually works before actually going deeper into the different steps themselves. So it goes like this. This is the longest quote in the presentation, so pay attention. So each participant knows of others it considers important. It waits for the vast majority of those others to agree on any transaction before considering the transaction settled. In turn, those important participants do not agree to the transaction until the participants they considered important agree as well, and so on. Eventually, enough of the network accepts a transaction that it becomes infeasible for an attacker to roll it back. Only then do any participants consider the transaction as settled. This is pretty much a rough explanation of how the consensus goes. The important part here is that what does consider important mean? Just a second. Yeah, okay. So what does considers important mean? So Stellar introduces a property definition called a quorum slice, which to humans pretty much translates to a trust group. It has open membership in the way that each node can first, one, decide who it trusts, and two, it is entirely flexible for it to decide which nodes to trust. There is no central authority that dictates who to trust and for whom. There can be multiple quorum slices, trust groups per node. For example, I can trust a group of 3 nodes over here and also require about 2/3 of agreement from that group, and also requires one third of agreement over another group that I trust as well. Think of it like a group of banks, for example. They don't necessarily have to cooperate. It is usually recommended that these quorum slices should be selected and constructed according to reputation according to reputation of businesses that control these nodes, and also maybe according to some financial agreement between these nodes. For example, if there's a business A and it needs to process payments and work with some reputable bank B and the credit union C, well, it is entirely logical that this business A will have B and C in its quorum slices, so that it requires them to acknowledge its transactions or transaction that it relays. For example, let's say we have a network of 4, so A could construct a quorum slice of only 3 out of 4 nodes in the system. This definition allows for quite complex and interesting trust structures in the network. For example, you could have a local or low priority tier of trust, a middle tier, and a top tier, where the top tier over there you require a large percentage of agreement over there before you can agree on consensus, and from the middle one you require only half of the nodes in the quorum to agree, and the top tier one could probably include a group of very large and reputable banks. But the low ones could probably include smaller organizations that you would also like to work with. Eventually, from quorum intersections, it is possible to achieve a system-wide consensus. So, for example, if I trust that guy and another guy trusts him as well, we can eventually agree, all the 3 of us, even though I'm not even familiar with the third one. So it results from intersections or overlapping of trusts. In the event where there is no intersections, where there are just different trust groups that are not familiar with each other by any path, there can be a case where it results in no consensus. And pretty much it means that the network is actually split just into 2 networks. Pretty much this is a very nice portrait of how it looks in a very simple way. So let's say that there is one quorum that results from all these nodes trusting each other, and there is also another one over here. But because they intersect with 3 nodes, it is possible to achieve consensus. But in the case where these groups have no one in common, it is not possible. The white paper also recommends certain ways to construct your quorum slices properly. So a couple of points. It recommends to first apply common sense, of course, and pick responsible choices. Make the trust groups, the quorum slices, large enough. And also make sure you're adding entities that are important enough not to risk their own reputations. Explain them more?
Yeah.
Do you have a more specific?
So in the scenario where we have disjointed quorum, and you said that it would split the network in half, right?
Yeah.
So in this scenario, will these 2 networks just continue going forward?
No, because the consensus favors agreement. Correct me if I'm wrong, but you're describing a case where the network did enjoy some sort of intersection before, and from some case, the nodes that were joining the entire network just disappeared, and now there is no connection between two quorums, right? This is what you were asking. So in this case, there would just be no more consensus. The consensus protocol, Stellar's consensus protocol, prefers the network to block and say there's some problem and I cannot agree and move on, instead of agreeing and screwing up later on. It pretty much favors safety over the network being live. Agreeing over terminating and moving on.
So you're saying that if you're taking cap theory, so Stellar is TP because it doesn't...
It is a bit wrong to compare this to cap theorem. It is not entirely the same. I don't want to go deeper into this because it's a bit of a longer discussion to explain why. It's not the right way to explain asynchronous systems only by cap theorems. I prefer to go by the FLP impossibility. Yes?
So there's no
No, there are blocks. Blocks are added according to consensus. It's just a property of the network protocol. It's just a container for transactions. They use a bit of a different terminology. They are adding ledgers, which if you compare it to Bitcoin terminology, adding a ledger is actually the same as adding a block. You add multiple ledgers over time. It is the same as blocks. It's just a container for transaction. Just a second? Yes. Yes, and I've actually, we've already been through the part where it shows where it is different. It is different is that there is flexible trust. It's not just one authority or a very small authority. Okay. You're asking how it is in real life, in practice? Okay, so currently, it's an interesting question. I will talk a bit about it at the end. I prefer to postpone this, but what the Federated Byzantine Agreement emphasizes is that it is only subject to market forces. So it could be that there will be only a single group in power, but it is definitely possible that there will be multiple groups. For example, there might be, if I go back to this, let's say that instead of having one tier, which is the dangerous case that you are suggesting, there are two. There's one with big banks, and there's one with non-profits. So if bank number 4 decides to double spend 1 trillion transaction to 7 and 8, it is entirely possible that others will also be dependent on the acknowledgement of the non-profits group that aren't drawn here. And this can prevent cases. In practice, I'm not entirely sure how it is constructed in Stellar, but I'm pretty much focusing on the technology here, not on the ecosystem that it is live today. It is still possible that there will be multiple interdependencies which will prevent centralized power. It is definitely possible, but it is the market that will decide upon this. It's definitely an issue, but it's in the hands of the market. Okay, so let's continue. What about bad nodes that operate in the systems? So Federated Byzantine Agreement defines nodes as befouled according to if they can undermine agreement in some way. Specifically, this includes multiple cases. If the nodes are faulty and they've subjected some sort of crash, if they are malicious and they are providing wrong information on purpose, and also good guys surrounded by bad guys. If a node is entirely well-behaving but is surrounded by ill-behaving nodes, it doesn't really matter if he's replying with correct information, because all the nodes surrounding him will just either want relay or relay whatever they want instead. the consensus model defines nodes as befouled and nodes as intact, which are not befouled. So pretty much well-behaving and ill-behaving nodes. So the solution to actually achieve consensus despite befouled nodes, faulty nodes, is to remove these nodes from quorum slices under certain reasonable conditions. Specifically, if they cannot undermine agreement, as long as two conditions apply. One, if it doesn't undermine quorum intersections. So removing, for example, if removing a node that a befouled node that is in the core critical areas interconnecting quorums, it might be impossible. But if it is not, it is entirely okay to just ignore this faulty node, and it is being recognized by providing inconsistent answers, and also including nodes that also include nodes that don't undermine other intact nodes from a quorum. These are the rules that need to be applied before removing befouled nodes from quorum slices. Yes, yes. As long as the befouled node is not in a very critical point, which can disconnect the entire network, if it's being removed, then yes, you can remove it. If it is there, it might be problematic and prevent the system to achieve consensus because everybody are relying on the same bad actor. This is entirely reasonable. So the core part of the implementation of the Stellar Consensus Protocol is called Federated voting. And before I elaborate on how the protocol actually works, I want to talk about this thing because this is the core part. The process of federated voting is happening multiple times over multiple steps, and it goes like this. So first there is the first step, which is voting over a certain value. All the nodes are voting over a value. Then they accept this value after seeing the votes, and then they confirm it. Confirmation is pretty much the same, is very similar to having a second vote over accepting. I will provide more information about this in the forthcoming slides. So let's explain it with a very simple example. Let's say we have a group order for food in the company, and there are two options. There's pizza and there's hamburger. These are the two options that are viable, that are okay to vote on. So the process pretty much looks like this. Let's say Vanessa is part of the group and which is trying to decide on one thing, one type of food to order. So at the beginning, it is entirely uncommitted. Then it has the choice to vote on one of the two options. There might be more, but in our case, there are only two. Then after voting, it accepts one of the options. And afterwards, this option, if there is enough agreement, this option will be confirmed, and we can move on. So to give a bit of details about the first step, so voting is entirely preliminary. It is not binding. It's pretty much, in our case of pizza or hamburger, and let's say Vanessa votes for hamburger. First of all, I want to emphasize there's a difference between voting, there's a difference between accepting something and voting to accept something. It pretty much in human speak, it pretty much means that you are open to the idea of agreeing on something. Let's say in our case that I would like hamburger, but it's different from saying I want hamburger. First I'm stating what I would like. So that's the difference between voting to accept something and actually accepting. If Vanessa is voting to accept hamburger, it pretty much means she's open to the idea that hamburger is a valid option for her. And also, it means that she will never vote for options that contradict the statement that will never contradict accepting hamburger. Since the votes are preliminary and are not binding, it is entirely possible that you will end up accepting another option, which happened in the second step, and I will explain how. So Stellar define a term called vote blocking, or V blocking for short. It is defined by, let's say there's a given node, A, which has its already defined quorum slices. So A's V blocking set, vote blocking set, is defined by creating it's constructed abstractly, but it's the node set that contains at least one node from each of A's quorum slices. So let's say if I am Vanessa and I have 3 quorum slices, I just pick 1 out of 3 and join them into a group, and this is my vote blocking group. The reason this is necessary is because it means that quorum slices can influence one another. Specifically, a V blocking set can block you from voting on something. It pretty much is the same like peer pressure, that let's say my entire group wants one thing and I want another, so because I want to achieve some sort of agreement, I will eventually converge on what they say because they've already agreed on something and I don't want to cause trouble because I am a well-behaving node. So the second step is using the V blocking concept for each node, which can prevent a node, for example Vanessa, from voting hamburger, which can cause her to accept pizza instead. So according to the rules that federated voting defines, Vanessa can eventually accept pizza even if originally she voted for accepting hamburger, if the following rules happen. First of all, she had never accepted anything contradicting pizza, let's say some other, even non-existing option like accept burrito. And if one of the 2 following rules happen. First, each quorum that exists votes for accepting pizza or has already actually accepted pizza. This pretty much means that they are already starting to converge. They've already converged and agreed on some value. Or there's another thing that can happen, that if there is a V blocking set for Vanessa that is already accepted pizza, this pretty much means that her quorum is already starting to converge on something. So either everybody had, or at least the critical part for Vanessa had accepted pizza. There's also another thing that is defined in the white paper where if an entire quorum is voting for the same thing, let's say the entire quorum is already voted to accept pizza, it is defined as ratifying accept pizza, and this process leads to the third step, which is confirmation, but it is entirely a requirement. The reason the third stage exists and we can't just finish after accepting something is that accepting is an internal process for a node. It's not actually acting upon it towards the entire network. It's pretty much a node understanding that there is some convergence, but it is, of course, mandatory that the network will communicate with one another and actually confirm to one another that they are agreeing on something. So this is the third section. Where you pretty much nodes broadcast their acceptance of a certain value and exchange confirmation messages. This pretty much shows other nodes that there is already agreement starting to take place in the network and convince nodes that are still in previous steps, because this is an asynchronous network, to agree on the same thing as well. So by actually confirming and by actually ratifying and broadcasting the networks, which means to confirm, you're actually applying peer pressure on the network and convincing others to agree with you as well on the same value. For example, Vanessa and her entire quorum will broadcast accept pizza, which will cause other quorums perhaps to agree as well. So this is the process. This is the process for federated voting, and now I will talk about the implementation that uses this theoretic model, which is the Stellar Consensus Protocol, also known as SCP. It's pretty simple. It has only 2 steps. It goes like this. The first step is to nominate a candidate. I will right after explain more verbosely what these 2 steps mean. So the first one is to nominate a candidate, and the second one is to conduct a ballot in order to commit a candidate, which means to update the ledger. These 2 steps involve federated voting separately. So there's federated voting for nominating a candidate for an update, and there's another federated voting for committing that candidate. So let's start with the first step. Just a second. I'll Are there any questions before I continue? Okay, so the first step, nominate. So in this process, in this step, the goal of this step is to produce candidates, which in our case means transactions for a ledger update. The current implementation just takes the union of all transactions that were submitted to the network. Then there's federated voting, the federated voting flow executed on the candidates. Pretty much think of a union, a single candidate being nominated as just a set of transactions, like a candidate block. So there's a federated voting over the candidate, and at the end, a quorum has confirmed a message to nominate a certain candidate, a certain block. This is the end of the first stage. But there can be a case where there are still contradictory nominations in the network. There can be split votes. There can be half of the people that want hamburger and another half that want pizzas. So there remains the question, then how can you resolve these kinds of arguments where there are multiple nominatees, sorry. So for this, this is the reason that the second step, the ballot, which is called the ballot, where eventually a single nominator will be chosen and all disputes can be resolved. The reason it's called the ballot is it uses the ballot-based system introduced by Paxos, which is a Byzantine fault-tolerant centralized system, centralized solution, sorry. You pretty much start, this stage starts in every node in an asynchronous manner. Once that node's quorum has agreed to, has confirmed to nominate a candidate block. In this stage, you can either confirm to commit a block or abort a block. What this means is that there's always a sequence of events through which intact nodes can reach agreement on and commit a value. This is the area where you are able to resolve cases where one side of the network wants that and cannot agree with the other side that wants something different. The way that it is achieved is via a process called neutralization, which allows for removing disputable arguments. For example, you can remove hamburger, just abort it out of the viable options, and leave the remaining options, only the other options. Instead, in our case, only the pizza option will be available. So, in short, if to summarize how the protocol behaves, that there's a first step of nomination where you produce candidates using federated voting, and then there is the second step where you can commit on a candidate via federated voting as well. And if a ballot has failed, you neutralize an option and retry again with a new ballot until everybody agrees on the same one. And this will eventually end because there is only a finite set of options that you can abort and leaving with only one option. The way that you neutralize options is that the implementation takes care not to contradict previously failed ballots, so it will only produce new valuable ballots, and not aborting things that have already been aborted before, just only aborting new things. In this way, all disputes can be eventually resolved, given enough time. This is pretty much the entire implementation of Federated Byzantine Agreement and the Stellar Consensus Protocol as its reference implementation. Are there any questions before we wrap up? Yes.
You didn't say what the ledger is. Is it the set of all accounts like in Ripple, or it's something else?
A ledger, Stellar calls a ledger which what is practically a block. So you add ledgers, but it practically is the same as adding blocks. A block is a container for transactions.
So it's a hash chain?
No, it's a blockchain. There's one block added over another, all the time. There is no tree. So before we wrap up, I want to talk a bit about Stellar's ecosystem because it has a bit of extra stuff in addition to the validator node, which is the core application. And it has just some interesting ideas. First thing is the Stellar's developer docs are one level above most other things I've seen in the crypto industry. It serves as a great example on how a company, specifically a cryptocurrency network, is trying to introduce its technology to developers. It is it's very easy for a newcomer to start working with the systems. I just recommend you to Google for Stellar Docs and take a look. So it's a really good example. So there's the Stellar Core application, which is the validator node, pretty much the equivalent of a Bitcoin core node, which is responsible for participating in consensus and replicating the information. The performance that they claim to have today is about 1,000 transactions per second, with an average block time of 5 seconds. And currently, the public networks, the public nodes that they publish on their website is, which I would take as the network size, at least the important part, is about 50 nodes. In addition, they have a distributed exchange integrated straight into their network. And they also have another application, which is an API frontend. It's called Horizon. And its goal is to abstract the whole asynchronous nature of working with the blockchain and makes it much, much easier and welcoming for newcomers to start submitting transactions and work with the network. So if I'm a mobile developer, I can just take their Java SDK and submit an HTTP request that submits a transaction, which is first, it's synchronous, and it will also reply with industry standard, in an industry standard way that all backend engineers know to work with. You'll have a status code and information. You don't need to implement any light clients or anything of the sort. You just need the HTTP reference implementation, and you can start submitting transaction, fetching information from the network, submitting to events, and so on. It's a very nice idea that they've implemented such a thing. In addition, they have another peripheral application that maps complex crypto addresses to human readable IDs like emails, and they have another compliance. Know your customer anti-money laundering application, which is required by banks in order to operate and provides KYC functionality. It goes hand in hand with the crypto address and with the crypto address mapping application. A simple topology of the networks look pretty much like this. So there's the core node, which validates and participates in consensus, and it talks with other core nodes in the system. There is the Horizon HTTP API gateway, which abstracts the whole block over there to the left, and clients communicate with Horizon, not even being aware of the network. No, you can still, like any decentralized network, still submit transactions to the validator nodes. It just makes it much easier for people who don't care. That's the point. This is why I wanted to talk a bit about it, because they've done plenty of work in introducing crypto to non-crypto developers. A few interesting links before we finish. So there's Stellar have a pretty short blog post that summarizes what I've talked about in the presentation. We will share the slides afterwards, and you can go there and take a look. There's also a YouTube video by David Macieres, which is the guy from Stanford that wrote and invented the Federated Byzantine Agreement and Stellar Consensus Protocol. There's another interesting blog post about talking about the FLP impossibility and Byzantine fault tolerance. And there's another interesting article that I found that compares different consensus models, specifically and talks about different permissioned ones. We're almost done. Just wrapping up and summarizing what we've been through. So we talk about decentralized consensus, about product requirements for decentralized consensus systems. We've introduced Stellar and its requirements, and we've introduced what a permissioned blockchain means. We've compared permissioned with permissionless. We've talked about and introduced a deep dive into Federated Byzantine Agreement and SCP. And I've given you a little glimpse of Stellar's ecosystem. One last thing, I just want to say that Kin, my company where I work at, we're currently hiring. We're looking for backend engineers, for DevOps people, mobile, content and product people, and design. So if you're interested or know anybody who's interested, please shoot an email over there. We're working here at this floor, at the other side of the floor. I really like the place. Yes.
So I'm under the impression that Stellar has a smart contract platform that works through the memos and transactions. Could you correct me if I'm wrong? Oh, you want me to repeat the question?
Yeah, sorry.
Okay, so I'm under the impression that Stellar has a smart contract platform that works through the memo that you can add to Stellar transactions. So what I want to know is if you could give a brief on how that works or correct anything I said that's wrong.
Stellar does not have smart contract functionality, but you can achieve some partial functionality using a set of transactions and time bounds and multi-signatures and so on. But it doesn't have smart contract functionality like Ethereum, for example.
Okay, could you give like a simple example of how something like that would work?
It's hard not to explain it in less than a few minutes. So there are other engineers here that you can also ask. They will give you a good question. There is a way, but it's not Turing complete or something.
What are you doing in Kin with Stellar?
What am I doing?
Not yourself, Kin. What do you, are there any particular projects that you use Stellar?
Originally, Kin, we did our token sale over Ethereum as an ERC20 token, but we are in the process of moving to using Stellar's blockchain. The core reason, we are in the process of doing this for the past half a year or so. The core reasons are that, first of all, it's quite stable. It's been running well since 2015, which is pretty nice, considering all other options which are pretty novel and new. It hasn't proven themselves yet. It has a pretty much predictable fee model, which is different from Ethereum, where it's very hard to create a business model where the fees can just inflate and deflate unpredictably. These are pretty much the core reasons. There are others as well. We have a blog, a technical blog for our team where we talk about it.
Could you give me particular projects, like actual use cases that you're using Stellar for?
We are currently running multiple experiments over. Kin is part of the Kik company, which is a messenger app. We are currently running experiments over Stellar technology on our own network, but using Stellar's technology. Where, for example, messages are actually transactions behind the network, and we pretty much run it with higher scale. This is one example. There are others as well. You can come over and I'll give you a few other interesting ones. Yes.
Okay.
Mobius conducted an ICO of using Stellar. Can you explain in short the way Mobius conducted the ICO using the Stellar network? Can you explain how it's done in a few sentences?
Yes. It's using the decentralized exchange functionality. There are multiple actions that you can perform on the network, not just submitting transactions. There are operation types. So there's the payment operation, which is like a Bitcoin transaction. But there's also a create asset operation where you can create a new token. So this is how they did it. And once you create it, you need to, afterwards, you need other accounts to trust the issuer of the account of the asset, which pretty much is a real world example is when you go and open a bank account, you trust that bank that issues, I know, like our currencies, an asset that is pretty much the credit for the currency that you're using in your country. So you give trust to the bank. So after an issuer creates an asset, you need accounts to trust the issuer, and then you can send payments for the asset. So this is roughly how you create an asset and distribute it, for example, in an ICO. Any other questions? Thank you very much.
Thank you very much, Ory, for a great presentation. You can